Dear students, welcome again. We observed the growth process explained in the Solow model. In this lecture, we shall see the Solow model of growth, which developed as an alternative to the Solow model. The objectives of this session will be to understand the meaning of technological progress, to understand the difference between endogenous and exogenous growth, to understand the effect of population, capital accumulation and capital labor ratio in the long term growth of economies, to understand why the growth of capital rich economies is lower than that of the developing economies. Fifth, to understand the meaning of convergence in the long term growth process. Before we proceed to understand Solow's growth model, we must know the meanings of technological progress, exogenous and endogenous growth. Technological progress is the term used for technical innovation which helps to increase output. Technological progress can be embodied or disembodied. Embodied technical progress means that machines embody inside them the technology which they are made up of. The vintage theory of capital focuses on the fact that a machine embodies the technology which existed on the date of its construction. Hence, with technical progress, as new technology is innovated, the old technology becomes obsolete and the machine loses its value. Hence, all machines made on different dates have different capacity to produce and hence cannot be aggregated as one single measure of capital. Hence, a separate production function is needed for each vintage, that is, machine with a different date of manufacturing or with a different embedded technology. New machines have new improved technology and thus imply technological progress. Disembodied technical change is purely organizational, which allows more output to be produced from unchanged inputs without any new investment. This refers to any kind of shift in the production function that leaves the balance between labor and capital undisturbed in the long run. The production function for such a technical change is written as Q is a function of capital K and labor L and of technical change A, or this function can be written as Q is equal to AT into the function of KL, where AT represents technical change which makes the inputs more effective in raising output. This technological change is organizational and does not require new inputs. Besides, technical progress can be neutral, labor saving or capital saving. Let us see what is meant by exogenous growth. Exogenous growth is a term used for growth that occurs owing to factors external to the model of growth. For instance, technological progress, which is exogenous factor, in some growth models can lead to growth. However, the idea of technological progress cannot be easily explained. Endogenous growth is a term used to explain that growth occurs owing to factors within the model. The Solow model is an endogenous growth model and it explains that growth is determined by the rate of savings and the capital output ratio which are determined within the model. Growth can occur when savings are used to invest in physical or human capital, and growth can also occur when the capital output ratio falls. Models based on this idea also explain that investments in human capital have positive spillover effects, and hence by increasing subsidies, by investments in education, investment in research and development, etc., growth can increase. These models thus assert that long run growth can depend upon policy measures which raise investments in certain sectors. Let us now proceed to understand the Solow model of growth. R.M. Solow's model of growth developed as an alternative to the Harrod-Domar model. Solow's model is based on diminishing returns to individual factors of production. Solow noted that any increase in quantity produced could come from one of the three sources as: first, an increase in labor L. However, due to diminishing returns to scale, this would imply a reduction in the output to labor ratio or the output per worker. Second, an increase in capital. An increase in the stock of capital would increase both output and the output to labor ratio given by Q by L, as capital helps to improve labor productivity. Third, an improvement in technology, which is denoted by A. This could also increase the Q by L ratio or the output per worker. If the production function is a typical Cobb-Douglas production function given by y is equal to a k raised to alpha n raised to 1 minus alpha, then the change in output is given by delta y upon y is equal to delta A upon A plus alpha into delta k by k minus 1 minus alpha into delta n upon n. It must be noted that in this Cobb-Douglas production function, it can be derived that alpha is the share of capital in aggregate output and 1 minus alpha is the share of labor in the aggregate output. In this equation, delta y upon y is the rate of growth of output, delta k upon k is the rate of growth of capital stock, delta n upon n is the rate of growth of labor force, and delta A upon A is the rate of growth of technological progress. Technological progress cannot be observed, and the rate of technological progress, which is the contribution of technological progress to output, is given as a residual after the contribution of labor and capital are subtracted from the total output. Hence, additional growth which is not owing to contribution of labor or capital is a growth owing to technological progress. Thus, the equation delta A upon A is equal to delta y upon y minus alpha into delta k upon k minus 1 minus alpha into delta n upon n is attained. The long term growth in Solow model. According to Solow, both capital and labor are used together to produce output, and inputs are subject to diminishing productivity. If there are many laborers and very little capital, then capital will help to enhance the labor productivity. In other words, productivity of capital will be higher. If there is less labor and more capital, then capital intensive techniques will be adopted. When a lot of capital is used, then its productivity will be lower and hence the capital output ratio will be higher. We may recollect here that a higher capital output ratio means that more units of capital are required to produce a unit of output. When productivity of capital is lower, more units will be required to produce a given output. In this model, the capital output ratio theta is endogenous. In the basic Solow model, the function may be given as y is equal to function of K and L, where Y is equal to total output, K is equal to capital stock, L is equal to labor supply. Note, we may also take the Cobb-Douglas production function to explain the Solow model. If we express the production function in per worker terms, which is similar to income per capita, then we obtain Y upon L is a function of K upon L and L upon L. Thus, it becomes Y upon L is a function of K upon L and 1. Now, Y upon L is nothing but output per worker, and we may represent it by small y or by gamma. K upon L is capital per worker, which we represent by small k or kappa. L by L is equal to 1. So, we get gamma is equal to a function of K by L and 1, which means that output per worker is a function of capital per worker. Change in capital stock can be given by delta K is equal to the change in capital stock, sigma is equal to the saving rate, which is a fixed fraction of income which is saved. Capital Y is equal to total income, small delta is equal to depreciation rate, and K is equal to capital stock. The equation for the change in the capital stock per worker will then be delta into kappa, which is equal to sigma into gamma minus n plus small delta into kappa, where delta kappa is equal to change in the capital stock per worker, sigma into gamma is equal to saving rate per capita, n is equal to the labor supply growth rate or the population growth rate. The capital stock per worker increases due to savings and decreases due to depreciation and an increase in the labor supply. We can use the Harrod-Domar equations to explain this. Recollect the equation in the Harrod-Domar model as K in time period t plus 1 is equal to 1 minus small delta into Kt plus sigma into Yt. Let us understand this equation. The stock of capital at the beginning of time period t plus 1 is equal to the stock of depreciated capital carried forward from the previous year t plus savings rate sigma Yt. Sigma is a constant fraction of income which is saved. We must note here that notation St means savings in time period t, which can also be expressed as sigma Yt, where sigma is the constant fraction of income y which is saved. Total savings is equal to fraction of income which is saved. If we assume that population Pt grows at a constant rate of n, then P in time period t plus 1 is equal to 1 plus n into Pt. This model assumes that growth of population translates in growth of labor supply or workforce. Introducing population growth in equation 2, we obtain 1 plus n Pt into K t plus 1 is equal to 1 minus delta Kt plus sigma Yt. Dividing equation 3 by Pt, we derive 1 plus n Pt into Kt plus 1 upon Pt, which is equal to 1 minus delta Kt upon Pt plus sigma Yt upon Pt, which is 1 plus n kappa t plus 1, which is equal to 1 minus delta kappa t plus sigma gamma t, where Kt divided by Pt is equal to capital per capita, which is denoted by kappa t, and sigma Yt upon Pt is equal to savings rate per person, which is denoted by sigma gamma t. This equation explains that the new per capita capital stock kappa t plus 1 can be obtained by depreciated per capita capital 1 minus delta kappa t and per capita savings sigma gamma t, but population growth drags down the growth of new per capita capital. The larger the population growth, the lower will be the per capita capital in the subsequent period and hence lower output. This is an important conclusion of the Solow model. Now, if no new savings or investments were made in the previous period and so depreciation is also taken to be 0, then equation 4 is given as 1 plus n kappa t plus 1 is equal to 1 minus delta kappa t plus sigma gamma t, which will turn as 1 plus n kappa t plus 1 is equal to 1 minus 0 kappa t plus 0. Therefore, 1 plus n kappa t plus 1 is equal to kappa t, or kappa t plus 1 is equal to kappa t upon 1 plus n. Thus, per capita capital in period t plus 1 is less than per capita capital in period t. Let us now draw a graph for equation 4. Look at this graph. The straight line through the origin shows amount of new capital required per person to keep the amount of capital per person constant. Since depreciation and increase in population both reduce the per capita availability of capital, a constant increase in capital or capital investment must take place to keep a steady state of growth. The curve represented by sigma gamma t shows the amount of savings rate per capita income. Savings rate is also the investment rate by macroeconomic identity S is equal to I. So, the curve sigma gamma t represents the investment per worker. At the per capita capital KO in the graph, the investment per worker is TKO, which is greater than the investment required to keep the capital per capita constant, which is given as QKO. Till K bar, the investment per worker is greater than the investment required to keep the capital per capita constant. At K bar, the capital required to maintain a steady state of growth is equal to the capital investment per person. If the economy is initially at a point on right hand side of K bar, then the investment per worker is lower than the investment required to keep the capital per capita constant. This means that the amount of capital per worker goes on declining in the economy. This declines till K bar. This movement is shown by the leftward arrows. Thus, K bar represents the steady state of growth where K t plus 1 is equal to K t. In other words, at K bar, the capital per capita is equal to capital required to maintain the capital labor ratio. When capital stock per capita is too high, the marginal productivity of capital is low and hence the output generation is lesser. This means when a country is richer and per capita capital stock is higher, the growth rate declines. At lower income, savings and investment will be lower and thus capital per worker will decline. But as these countries raise their savings and capital formation, the per capita availability of capital rises and growth tends to rise. Hence, all economies converge towards the steady state in the very long run. Hence, we can see that each nation requires an appropriate stock of capital to maintain its labor productivity and output. Growth will be very strong when countries first begin to accumulate capital and will slow down as the process of capital accumulation continues. Growth of capital abundant countries was stronger in the 50s and 60s than it is now. Look at the graph here. A higher saving rate sigma increases the investment per worker and it exceeds the investment required to keep the capital stock per worker constant. Thus, the capital stock per worker increases till a new steady state is attained, shown here as K double bar. Now, look at this figure. As the population rises to n dash, the investment per capita becomes lower than the investment required to maintain the capital per worker. Thus, capital stock per worker keeps declining from the steady state K bar to the new steady state K double bar. Let us summarize. Hence, dear friends, let us summarize that technical change may be embodied or disembodied. Growth can be exogenous or endogenous. In the Solow model, any increase in quantity produced could come from one of the three sources as an increase in labor L, which is subject to diminishing returns to scale, which imply a reduction in the output to labor ratio. Second, an increase in capital. An increase in capital would increase both output and the output to labor ratio as capital helps to improve labor productivity. Third, an increase in technology A could also increase the output per worker. What should we remember here? We must retain the Solow equation 1 plus n kappa t plus 1 is equal to 1 minus delta kappa t plus sigma into gamma t, which explains an important conclusion of this model that the new per capita capital stock kappa t plus 1 can be obtained by depreciated per capita capital 1 minus small delta into kappa t and per capita savings sigma into gamma t, but population growth drags down the growth of the new per capita capital. The larger the population growth, the lower will be the per capita capital in the subsequent period and hence lower output. So, friends, we end today's lecture here, and in the next session we shall see another model of growth. Thank you.